Okay, in this lesson we are going to continue on with our discussion in regard to our correlation and regression. So we're going to be working in StatCrunch under regression again. Okay, so what we're going to be doing here is we're going to look at that correlation. If we find that we do have somewhat of a correlation between two different variables, we want to try to find the equation of what we call that regression line or a line of best fit or a trend line. There's different terms for it. But we want to find the equation that best fits the points that are in our scatter plot of our paired data. We could come up with two equations. Our first equation would be representing our sample, the equation for our sample data. We have y hat is equal to b of o plus b of 1x. If you're creating the equation for your population, it would be capital Y is equal beta 0 plus beta 1 times x. Now, I want you to recognize that we're going to look at the sample one most usually. This b of o is your y-intercept. The b of 1 is your slope. And so that is very similar to what you probably came across in your algebra class. I think possibly most of you recall y equals mx plus b is that slope-intercept form of a line. But in that scenario, you have your x term first usually, followed by your y-intercept. It's the same information, it's just the order has swapped when we're working with statistics. So we're going to be looking at this form. Okay, so y hat is the response or the dependent variable, and I think that's probably not news for many of you. X is the explanatory or the independent variable. Many of us look at that as x is always going along the horizontal axis, y is along the vertical axis, but I want you to focus in on what is dependent and independent. Okay, regression equations are often useful for predicting the value of one variable, and we're going to see how we can do this given one value, a value for the other variable. We're going to do this in StatCrunch. But properties and requirements, you are not to use a model if it is not a tight fit to the data. In other words, if you have that picture where you have, data all over the, data points all over the scatter plot, it's generally not good to try to use a regression line. In that case, you're asked to use what you call y bar, which is the mean of all the y values instead. In other words, you're going to take all your y outcomes and average them, and that's what you're going to use for your y hat or y bar. We're going to use the regression equation only if the linear correlation R indicates there's a strong correlation, and that's kind of relative depending upon the sample size. We're only going to use a regression line if they do not go to predict new values, if we're not trying to predict too much beyond the scope of the data. Anytime you get outside the scope of the data, that's called extrapolating. There could be a variance there that you're not taking into account. Okay, for each fixed value of x, the corresponding values have a normal distribution, and that's what this picture here is trying to depict here. I want to talk about these last couple steps, and then I'll go back to this picture. For different fixed values of x, the distributions of the corresponding y values all have the same standard deviation. That's where you get this normal distribution. So basically for any value x, so for this value x, I'd have a vertical line going through here. Let's say this was x equals 3 or whatever. We'd have all these different outcomes for y, but we'd see that they would cluster and get close to the y that is on this point. So we'd see that distribution for y would follow this normal distribution, and the standard deviation there would be the same. So we're going to find that that distribution would be so at any point along that line. For the fixed values of x, the distributions of the corresponding y values have the means that lie on the same straight line. In other words, this y on this line is the average of all the y's for that had that explanatory variable of x. So I was trying to make that point before when we were talking about the regression line, that the slope is actually the average of all of these y outcomes from our data. That's what we're hoping for a tight fitting piece of data or set of data. In StatCrunch, again, we're going to use the same thing. Stat, regression, simple, linear, but this time I'm making a point of you're going to choose the column for the explanatory value x, and the column that is the response value y. Just making a different point of that y is totally dependent upon x. This time we're going to choose the predict y option and input a value of x to predict an outcome if needed. But I want to go back to our problem from last video and put this up here. This was the output, and we kind of ignored some things on here because last time all we were concerned about was getting the coefficient R, correlation coefficient R, possibly R squared, which was that coefficient of determination, and then also looking for a test statistic. Again, I was asking you to look at the slope row, looking at the t-stat for the slope, and then the p-value. That's all we looked at on this. But here in this section, I want you to take a look at this line right here. This is telling you what your regression line is. Life expectancy is equal to 68.7 plus 0.42 times the gross domestic product for that country in that year. So we could use that formula to speculate the life expectancy for other countries that maybe aren't part of this list. And I need to show you how you do that. But again, this chart here, the parameter estimates, that's estimating that the intercept is 68.7. We found that right there. And then our slope, its estimate is 0.42. We found that right there in the equation. So you can find that in two different places in this display. And this is a whole lot easier than what many of you did in your algebra classes for the same type of thing. But I want to show you how you would go ahead and predict a value. So in our notes, we're going to try to predict 16.5. In other words, we want to predict the life expectancy for a country with a gross domestic product of 16.5, 21, and then 21 or 28.5. I could go back in here to options, and I want to click edit. We're going to go down here to look at graphs. You see how default it automatically fitted the line plot? This time I want to go ahead and have it do, actually what I want to do is I want it to predict, I want to go to the prediction, the Y value, and I want to predict for 16.5. I'm not going to worry about the graph. 16.5, and I want to hit compute. And now I get that down here in my output. For the value of 16.5, my predicted Y outcome is 75.6. You could also use your calculator and plug it in and find it. Again, we could go over here and look at this line and kind of project where it might be, but hey, do you see here that 16.5? I'm down below here. I'm far to the left. So what I'm trying to point out here is that this data value is below the scope. Now I also plugged in 21, and you can do this on your own. When I plug in 21 is 77.5. When I plug in 28.5, that's above the scope. So if I'd go back to my graph here, I can see 28 fell out here, but 20 fell in this range. It's not usually a good idea to use the equation to project below or above the scope of your graph or your original data. Okay, so we use that, and then I'm going to come over here and talk about how we can interpret the slope. The marginal change in a variable is the amount that it changes when the other variable changes by exactly 1 unit. That 1 unit is the slope, and the regression equation represents that marginal change. So the slope is the marginal change. And in our example, what is the marginal change in our gross domestic product and life expectancy data? You could expect that you would live 0.420 years longer for each $1 trillion in gross domestic product. And we get that from the equation here, this slope. For every $1 trillion of increase, you could expect to live that much longer. Okay, influential points are points that are strongly affect the graph. Your textbook does this example where they try to correlate, the chocolate consumption of a country with the number of Nobel laureates or candidates for the Nobel Prize. Kind of a crazy correlation there, but they came up with this correlation. And if we projected a point of 50 here, that would be really considered an outlier in this case, but it'd be a very influential point, and therefore it would greatly impact this regression line. That's about as much as I want to talk about influential points. I really want to get into the residual. A pair of x and y values, the residual is the difference between the observed sample value of y and y hat, which is the y value for the predicted, that is predicted by the equation. So in this small little chart here, we only have 1, 2, 3, 4 points on here. we can see that this regression line kind of goes right smack through the middle of them. Kind of a general rule of thumb in eyeballing these things is that your regression line should have half the points above and half the points below. If it's different than that, the lower side, the side that has the fewer number of points, those points would generally be farther from the line. But that's one way to think about it, because what's happening is you're looking at the difference between the data value and the point that was projected on the regression line. And then you're looking at trying to average all of these so that we have the least, our least regression line here, or our regression line that we've plotted here is going to have the smallest residual. And so the residual is equal to the observed y minus the predicted, and this would be algebraically how you would represent that. So technology, in this case StatCrunch, is going to provide a regression line that meets the least squares property, and that the sum of the squares of the residuals is the least sum possible. So again, they do that squaring thing because sometimes some of these points are below and it'd be a negative difference, and some are above and it's going to be positive. So again, we square and sum and we come up with this least squares property. Okay, so a residual plot is a graph of the points where we are plotting for every x, we're looking at that residual, or the difference between the 2 points, between the 2 y's, whether it was the projected y or the actual y's. When analyzing residual plot, the point should not have any obvious pattern. That's what I'm trying to show you on these 2 examples here. In other words, there should not be an obvious pattern, and it should not become wider as you're viewing this from left to right. So on both of these this is our original data plot. This is another original data plot. Both of these have correlation coefficients of positive 8 and negative 8. So in other words, this one rises going left to right, this one falls going left to right. This one's it's a pretty tight fit of an R of 8, a correlation coefficient of 8 in both of these cases. But if you look at this first one, there's a little bit of a curve to these points that you might miss if you're not really looking closely. But if you look at the residual, what the residual does is it takes this regression line and lays it out as a horizontal line so that you can see the points that are above are on one side of the line, and the points that are below, or on the other side of the line, are now below. And so you can see that definite curve there in your residual just really accentuates the difference here, that this set of data follows a curve. So this is, in my mind, this would be a possibly quadratic relationship. So I would move away from trying to do a linear regression and do a quadratic regression. But you're not going to need to worry about that for this class. Okay, so you just need to be able to recognize if it's a good fit or not and be able to use and interpret a residual plot. Now in this one, as we're going left to right, it's going to have a negative regression, R, correlation coefficient R. But if you see here, these kind of widen as you go from left to right. The distance from the regression line increases. That becomes really, really obvious when we take this regression line and lay it out level, and then we see the points that fell below and the points that fell above the regression line. So this, you're going to see your y-axis is going to be negative values up to 0 and then positive values, because this is saying the movement from the regression line. So I wanted to give you those two to recognize what you should look out for when you're interpreting a residual plot. Then I want to go back to our example and actually show you how to do this. This is what I almost showed you a little bit too early in the game. So I'm going to go back to Options, I'm going to go to Edit, and this time I want to go down to my graphs. It automatically fitted the line plot, but I want to go down and I want to look at the residual plot, and that is residuals versus the x values. So I'm going to click on that and click Compute. Nothing changed here in my output in the original screen, but if I go to the second screen, this is an example of my residual plot, but ours doesn't show that regression line going across as a horizontal line, so you can see that would be right at 0. So on this one you can see that we don't have any pattern here. Doesn't get wider going left to right, it doesn't follow a curve or anything. So this would be an acceptable residual plot. There's no pattern, there's as many as above as below, the distance, we've got one here that is really far, one here that is really far, no other patterns. So I'd like you to record this particular residual plot in your notes so that you have an example of what an acceptable residual plot would look like.